Hello, awesome chemists. Today we're going to talk about Chapter 13, which is states of matter. We actually just finished talking about gases, so we are mainly talking about condensed states of matter, which are solids and liquids. They call them condensed states of matter because particles are condensed, they're close to each other. In solids and liquids versus in gases, they are far apart, so they're not considered condensed in gases. Factors that affect whether a substance is going to be solid, liquid, or gas are the chemical makeup, specifically the strength of your intermolecular forces. So if a substance has weak intermolecular forces, it's likely to be a gas because particles are not really attracted to each other, so it's easy for it to separate and turn into a gas. If a substance has very strong intermolecular forces, then the particles are going to be really attracted to each other, and it's likely to be a solid. If it's in between, then it's likely to be a liquid. Temperature, of course, affects the state. So at very cold temperatures, your substance is likely to be a solid, but at very high temperatures, it's likely to be a gas, and in the middle, it's likely to be a liquid. And then the pressure, the higher the pressure you put on something, the more compressed it's going to be, and it's likely to be a solid or a liquid, versus low pressure would mean it's likely to be a gas. So let's review real quick the differences between solids, liquids, and gases. I'm going to let you write down the notes here. I'll just talk about them and you write the notes. So let's start with the position of the particles. These are close to each other. They're ordered in a nice crystal with repeating patterns. In a liquid, they are close to each other still, but they are random. In gases, they are far apart and random. In terms of motion, solids vibrate in place. Liquids are able to slide past each other. And then gases move rapidly and randomly. In terms of shape and volume, solids, because they're close together, have a definite shape and volume. They're close together and they vibrate in place, so they have a definite shape and volume. Liquids are close together, so they have a definite volume, but because they're random and they're able to slide past each other, they can take the shape of the container. And then gases take the shape and the volume of the container. Gases can flow and diffuse. Liquids can flow and diffuse slowly. And solids cannot diffuse or flow. Because of the large spaces between them, gases are compressible. Liquids are almost not compressible because there's not much space to compress them together. And then solids are not compressible. In terms of density, solids and liquids have similar densities because the spacing between the particles is similar. For most substances, the solids are just slightly more dense than the liquids. An exception to that is water, of course, where the liquid is more dense. But most substances, the solid is slightly more dense than the liquid. The liquid is slightly less dense than the solid. The gases have way lower density than the solids and the liquids. In terms of potential energy, solids have the least amount of potential energy, followed by liquids, and then gases have the highest potential energy. So that's a quick review of the three states of matter. Let's now focus on liquids. We're going to spend a few days on liquids, and then, the last day of the chapter, we're going to focus on solids. So some properties of liquids that we just mentioned. So they assume the shape of the container, they're not compressible, almost not compressible, they maintain a constant volume, and they flow. The biggest difference between gases versus solids or liquids is that because the particles are close to each other in solids and liquids, the intermolecular forces now become significant. Remember with KMT, with kinetic molecular theory, we said that the interaction, the intermolecular forces between gas particles is negligible. We ignore it because the particles are so far apart, and so there's not much attraction between the particles. But once you bring them close to each other, then those intermolecular forces become significant, and these intermolecular forces affect a lot of properties that we see in liquids and in solids. So let's review the different types of intermolecular forces real quick. So we have dipole interactions. So dipole means two sides, and so these occur between polar molecules, sided molecules. So right here, the positive end of one molecule is attracted to the negative end of the other. And so there's attractions here and here and here and here. The more polar it is, the stronger the polarity, the stronger the intermolecular forces in terms of dipole moment. Then we have hydrogen bonding. Hydrogen bonding are a type of dipole, but they occur in very polar molecules. They are molecules that contain an HF bond, an HN bond, or an HO bond, just like water here. Now, this is not the hydrogen bond. It is, again, the attraction between one water molecule and another water molecule. So this attraction right here, that is your hydrogen bond. And it's the same idea as dipole. The partial positive end of one molecule is attracted to the partial negative end of the other molecule. Just because that partial positive and partial negative are a little bit stronger, that causes these hydrogen bonding to be a little bit stronger than a regular dipole interaction. And then finally, London dispersion. These occur in all molecules. So if you have something that's polar like water, it also has London dispersion. But it's negligible, it's very weak compared to the other two. And so we really only look at it or consider it significant in nonpolar molecules that don't have anything else. And so the idea here is the dispersion of the electrons. So if you look at two molecules here, let's say these are nonpolar, and because of the electrons moving very randomly, just for an instant, by coincidence, they might be concentrated in one area of the molecule than another. And so if this happens, and you get more electrons here on that side, then you get an instantaneous, just for a second, split second, a partial negative here. And that causes this to be partially positive because the electrons are not distributed there as much. Well, what that does is it causes the neighboring molecule to do the same thing. The electrons in this molecule are going to be pushed this way as well. And so now you're going to have a partial negative and a partial positive here as well. And so now that attraction between the partial positive and the partial negative right here, that is your London dispersion force. It is extremely weak because it happens for a split second and stops, happens for a split second and stops, because it is happening due to the random motion of the electrons. It's not a permanent partial positive or negative like in these. It is just an instantaneous happens and off, and so on. In terms of London dispersion forces, like we said, they occur in all molecules. The molecules with more electrons and the larger molecules have stronger London dispersion. Let me repeat that. So in terms of London dispersion, the more electrons a molecule has, the stronger the London dispersion. So if we're comparing, for example, fluorine F2 versus bromine Br2, Br2 has stronger London dispersion than F2 because bromine is larger and has more electrons. And so that polarizability, that idea of the electrons being in one area more than the other, is more likely to happen with bromine, where you have more electrons. And it's also more likely that because you have more electrons, that partial positive and partial negative are bigger or stronger. And so with London dispersion, the more electrons, the stronger the London dispersion. Okay, so some properties are affected by those intermolecular forces. One of these properties that's affected by intermolecular forces is viscosity. And viscosity is the liquid's resistance to flow. And again, it has to do with these intermolecular forces. So I have a substance here that is extremely viscous. You can see it is flowing very, 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 very slowly. So that would be something that is very viscous. It has high resistance to flow. So let's think about this in terms of intermolecular forces. Let's say your substance has very strong intermolecular forces. That means the particles are very, very attracted to each other. Well, if they're very, very attracted to each other and they're stuck together, so it is going to be harder for them to flow and they are going to be more viscous. Imagine if you were in class and the bell rings and you all rush out, versus the bell rings and you all rush out holding hands. because you guys just love each other. You want to hold hands all the time. So imagine if you had to hold hands and go out of the room. You're going to be much slower if you're holding hands. So same idea with particles. The more attracted they are together, the closer they're going to be, and they're going to flow slower and be more viscous. So the stronger the intermolecular forces, the higher the viscosity. Okay. Some things that we think of as viscous: syrup, honey, shampoo. They flow very, very slowly, similar to this here. Things that flow very fast are acetone or alcohol. If you ever had to pour acetone or alcohol, it just flows out. It's very, very fast when it flows, and so it's not viscous at all. Okay, surface tension is another property that is affected by intermolecular forces. And surface tension is the idea that a liquid has a kind of like a membrane or a barrier at the very surface of it. So if you look here, let's look at this particle right here in the middle. It is attracted to, because of intermolecular forces, it's attracted to particles all around it. So the attraction is everywhere, right? But take a look at a molecule that's at the very top. If it's at the very top, it is only attracted inward. And so those particles that are at the surface, they are only attracted inward, so they're kind of like huddling over the surface of your liquid, and that makes like a membrane almost, or a barrier at the surface of your liquid. The stronger these attractions, the stronger that barrier is. If you look at this picture, this is mercury. And it has a very high surface tension. You can see it's beating up. Water has pretty high surface tension as well. That's why, like, when it rains on your windshield, you'll see like drops of water. That's because the water particles have strong attractions to each other, strong intermolecular forces. So they attract each other and kind of huddle in and make a drop as opposed to it going flat. So I want you to try this at home. Put a drop of water on a table, put a drop of oil on the table or on a plate or something like that so you don't make a mess, and watch both. You'll see that the water beads up as a drop versus the oil is kind of flat because water has stronger intermolecular forces than oil does, and so it's more likely to form that surface or that membrane. So the stronger the intermolecular forces, the stronger or the higher the surface tension. I want to show you, I have a jar here. It's a mason jar, and it has a mesh here. So I'm going to fill this with water. So turn my faucet on. Put some water through. And the water's going through because of that mesh. That's probably not. So it's filled with water. And now what I'm going to do is I'm going to flip it over. You see that I'm flipping it over, but the water is not falling. That's because water has very high surface tension, so it's creating a membrane that's huddling, that's causing a barrier here. If I break that surface tension by going like this, then it spills. And so water has pretty high surface tension. Because of surface tension, the water is able to go up the roots of plants with capillary action to allow our plants to get the water they need. So that's a great thing about water, is that high surface tension. If you've ever, like, I know, little kids sometimes look at the insects that go on water, and then they use soap. The soap basically disturbs that surface tension, disturbs that membrane, and so if you put soap and have the insect on there, it drowns. So that's because of the surface tension of water. Okay, so what we just talked about is if you have strong intermolecular forces between your particles, you're going to have high viscosity, high surface tension. If you have weak intermolecular forces, you're going to have low viscosity and low surface tension. So on the test, I could give you 2 or more molecules and ask you to rank them in terms of intermolecular forces or in terms of viscosity or in terms of surface tension. And you would do all of them the same way. Whether I ask you for surface tension or viscosity, you have to figure out what types of intermolecular forces they have first. So what you want to do is you want to draw these and come up with the types of intermolecular forces. So here's CH4. Here's C2H6. Here's water. Here's HBr. Methanol. And then we have ethanol. Okay, so first thing you want to draw them and then decide what type of intermolecular forces they have. So let's go through each of these and figure out what type of intermolecular forces they have. Let's look at CH4 first. So CH4 is nonpolar, and so the only type of intermolecular forces it has is London dispersion. C2H6, same thing, nonpolar, so it also has London dispersion. Water is polar, and it has hydrogen bonding. HBr is polar, it has dipole. And then both methanol and ethanol are polar and they have hydrogen bonding. So we are ranking them in terms of weakest to strongest. So weakest types of intermolecular forces would be London dispersion. So between this one and this one, they both have London dispersion. CH4 would be the weakest, followed by C2H6. Why? Because C2H6 is larger, has more electrons. And so the more electrons you have, the stronger your London dispersion, meaning that you have more electrons that could go in one side of the molecule more than another to create that temporary dipole. So out of these two, methane is the weakest, followed by ethane. Next, in terms of intermolecular force strength, would be dipole. So HBr would be number 3. And then these 3 are all hydrogen bonding. What do you think? Which one's the strongest? Which one's the weakest out of these? So this one would be number 4. This one would be number 5. And this one would be number 6. So let's talk about why. So let's talk about water. So hydrogen bonding, remember, is the idea where you have partial positive of one molecule attracting the partial negative of the other molecule. So you have partial positives here and a partial negative on the oxygen. So this partial positive can attract another water molecule, this partial positive can attract another water molecule, and this partial negative can attract another water molecule. So these dotted lines that I drew, these would be sites where you can have hydrogen bonding with other water molecules. Now let's look at these here. There's a partial negative on the oxygen, partial positive here, partial negative on the oxygen, partial positive here. So here, this can attract another molecule, this can attract another molecule, but that's it. The rest of this doesn't really have partial positives and negatives. Same thing with this one. Oh, I'm so sorry, I didn't draw this right. This is the C2H5OH, and this is the CH3OH. I drew them the same way. So where you have partial positives and negatives, so right here and right here, those would attract other ethanols. But right here, this part of the molecule does not really attract anything. Same thing here. Right there, it can attract another methanol, and right here it can attract another methanol because of those partial positives and negatives. But the rest of it, where the carbons and hydrogens are, there's not really partial positives or negatives. There's not much attraction there. So we would say water has more sites for hydrogen bonding. These right here inside of the molecule, this is not a hydrogen bond. So don't say that water has 2 hydrogen bonds versus this one has 1. That's not true, because these are not hydrogen bonds. The hydrogen bonds are the attractions between one molecule and another. So we say water has more sites for hydrogen bonding compared to ethanol or methanol. So that's why this one is the strongest. Now, out of these two, you'll see that they're very similar. Where the hydrogen bonding is very similar, looks pretty much the same. The only difference is that this has an extra CH3 there. So this one would be a little bit stronger because remember that these have hydrogen bonding, but they also have London dispersion. Remember, London dispersion occurs in all molecules. And so if they look really similar like this, then you go with the bigger molecule, the one that has more electrons, because not only does it have the hydrogen bonding, it also has more London dispersion than this one does. So this one would be number 4, this one would be number 5, and then water would have the strongest intermolecular forces out of these. So let's say I ask you this question in terms of rank them in terms of lowest to highest viscosity. You'd do the same exact thing. You would draw them, you'd figure out what type of intermolecular forces they are, you would rank the intermolecular forces, and you'd say the one with the weakest intermolecular forces has the lowest viscosity, the one with the highest intermolecular forces has the highest viscosity. And same thing with surface tension, of course. All right, I hope you guys have a wonderful rest of your day.